These are the answers to the AP Chemistry packet that is entitled Unit 9, Summative Assessment Practice. On this slide, you can see Unit 9 at a glance. Unit 9 is entitled Thermodynamics and Electrochemistry. In this video, I will present practice problems that cover the topics in Unit 9. This video should help you to prepare for the Unit 9 summative assessment. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Okay, let's get started. The instructions that you see on this slide are the same instructions that you will see on the AP Chemistry free response section. Show your work for each question in the space provided. Examples and equations may be included in your responses where appropriate. For calculations, clearly show the method used and the steps involved in arriving at your answers. You must show your work to receive credit for your answer. Pay attention to significant figures. Question 1 says the following. Answer the following questions based on the reaction represented by the equation shown above. The values of the standard molar entropies of the substances involved in the reaction are given in the following table. Part A. Use the data in the table to calculate the value of the standard entropy change, or delta S, in units of joules per Kelvin mole of reaction for the reaction. Show your calculations in the space below. So this question falls under topic 9.2, absolute entropy and entropy change. The entropy change for a process can be calculated from the absolute entropies of the species involved before and after the process occurs. So you can see it takes the general form of products minus reactants. And if you look on the AP Chemistry equations and constant sheet, you will find this equation listed in the section entitled Thermodynamics and Electrochemistry. So before we do the products minus reactants calculation, I just want to remind you of a common mistake that students make, and that is they forget to use the coefficients from the balanced equation when they're doing their calculation. So the fact that there is a 2 as a coefficient for hydrogen in this chemical equation, that means that when we do our math, we need to multiply the value for the standard molar entropy for hydrogen by 2. So products minus reactants in this case would be 239.9, which is the standard molar entropy for methanol, or CH3OH, and that is our only product, and then minus the sum of the standard molar entropies for the reactants. So it's going to be 197.7 for carbon monoxide gas, and then it's going to be 2 times the number for the standard molar entropy for hydrogen gas, so 2 times 130.6. And if you do that math on your calculator, hopefully you will get the correct answer, which is negative 219, and the units are joules per Kelvin mole of reaction. So this is the answer to part A. Now, before we take a look at part B of this question, let me show you on this next slide. This is topic 9.1, Introduction to Entropy. And what I've highlighted on this slide is the following sentence. It says, for reactions involving gas phase reactants or products, the entropy generally increases when the total number of moles of gas phase products is greater than the total number of moles of gas phase reactants. So if that sentence is true, then the reverse of that sentence is also true. And that's what's going on in this reaction in question 1. So we start with 3 moles of total gaseous reactants, and then it ends with 1 mole of gaseous products. So instead of the entropy increasing, as it says in that highlighted sentence from the essential knowledge statement for topic 9.1, we can see in our calculations that the entropy actually decreases. So why does the entropy decrease for this reaction? Well, when you go from 3 moles of gas for the reactants to 1 mole of gas for the products, now we have a smaller number of possible arrangements of the particles, and so the entropy decreases. I just wanted to show you that information to help you understand that that's why the delta S, or the change in entropy, was negative for this reaction. Now, let's take a look at part B of this question. In part B, it says, circle one of the following choices that best describes the thermodynamic favorability of this reaction. And our four choices are not favored at any temperature, favored at all temperatures, favored at high temperatures, or favored at low temperatures. To answer this question, we should consider the sign of delta H, or the change in enthalpy, as well as the sign of delta S, the change in entropy. So we were given in this question that the delta H is negative. And then we just determined by answering part A that the sign of delta S is also negative. This question falls under topic 9.3, Gibbs free energy and thermodynamic favorability. And so this chart shows the sign of delta H, the sign of delta S, and then whether or not the reaction is going to be thermodynamically favored at all temperatures, no temperatures, high temperatures, or low temperatures. So because both delta H and delta S are negative, that means that it falls under the category of being thermodynamically favored at low temperatures. So take a look at the Gibbs free energy equation at the top of this slide. We have a negative delta H, we have a negative delta S. So what is the sign of delta G? The answer is it depends on the temperature. So as long as we have a relatively low temperature, then the sign of delta G should be negative, and the reaction would be thermodynamically favored. But if the temperature is relatively high, then what can happen is the sign of delta G will change from being negative to positive. And so if the sign of delta G is positive, then the reaction is not thermodynamically favored. So favored at low temperatures, not favored at high temperatures. So the correct answer to part B of this question is favored at low temperatures. Now let's take a look at part C of this question. In part C, it says calculate the value of the standard free energy change, delta G, for the reaction at 298 Kelvin. Show your calculations in the space below. So to do the calculation in part C, we will use the Gibbs free energy equation involving delta H and T delta S. So as you can see, this equation is listed on the AP Chemistry equations and constant sheet. A common mistake that students make on the AP Chemistry exam is that when they use the Gibbs free energy equation, they don't pay attention to the units. So I'm encouraging you to pay attention to the units, and what I mean is, let's take a look at the units of delta H. So as you can see, the units of delta H are kilojoules per mole of reaction. Now take a look at the units for delta S. Now the units for delta S are actually joules per Kelvin mole of reaction. And if we read the instructions in part C, it says calculate the value of the standard free energy change, or delta G, in units of kilojoules per mole of reaction. So the conversion factor to go from joules to kilojoules would be that there is 1 kilojoule for every 1,000 joules. That means I'm going to take negative 219 and divide by 1,000. And when I do that, I get negative 0.219, and now my units for delta S are kilojoules per Kelvin mole of reaction. Now let's plug in these values into the Gibbs free energy equation. So delta G equals delta H, which is negative 90.2 kilojoules per mole of reaction, minus T delta S. So the T, the temperature, is 298 Kelvin, and then the delta S with the proper units is negative 0.219 kilojoules per Kelvin mole of reaction. And as you can see, the units of Kelvin will cancel out. So when we do this math, we get our answer, which has the proper units of kilojoules per mole of reaction. So the answer to part C works out to be negative 24.9 kilojoules per mole of reaction. Now let's take a look at the last part of question 1, which is part D. Part D says, is the reaction thermodynamically favorable at a temperature of 298 Kelvin? Justify your answer. So as you have learned in topic 9.3, if the sign of delta G is negative, the forward process is thermodynamically favored to occur, but if the sign of delta G is positive, then the forward process is not thermodynamically favored to occur. So because we know that delta G is negative, the answer to part D is the following. Yes, the reaction is thermodynamically favorable at 298 Kelvin because the sign of delta G is negative, or delta G is less than 0. Now let's take a look at question 2. Question 2 says, answer the following questions related to the information shown above. Part A, use particle level reasoning to explain why the sign of the standard entropy change, or delta S, is negative for this reaction. So this question falls under topic 9.1, Introduction to Entropy, and the first sentence in that first essential knowledge statement says, entropy increases when matter becomes more dispersed. Now let's take a look at the reactants and the products for this chemical equation. So for the reactants, we have a total of 3 moles of gas. And for the products, we have 1 mole of solid and 1 mole of liquid. So again, back to topic 9.1, it says that when we change from a solid to a liquid, or from a liquid to a gas, this results in a dispersal of matter as the individual particles become freer to move and generally occupy a larger volume. But that's not what's happening in this particular equation. So as I show you on this next slide, this was from my video for topic 9.1. And let's take a look at what happens if we go from a gas to a liquid, or from a liquid to a solid, or from a gas to a solid. What happens is that the matter actually becomes less dispersed and more ordered, and the particles actually have less freedom to move and spread out. So if that's what's going on, gas to liquid to solid, then the entropy decreases and the sign of delta S would be negative. So for example, liquid to solid, gas to liquid, gas to solid results in a decrease in entropy, or a negative delta S. So it does say in part A to use particle level reasoning. That means that in your answer, you need to describe the behavior of the particles. You can't just talk about the phases of matter. You also have to explain what's happening in terms of the particles and the property of the particles. So here's what I'm going to go ahead and say for my answer to part A. I start with 3 moles of gas on the left side of this equation, and the particles are more dispersed, or you could say there's a greater number of possible arrangements. But then for the products with 1 mole of solid and 1 mole of liquid, now the particles are less dispersed or more ordered, and so there is a smaller number of possible arrangements. So in my answer to part A, I'm describing the phases of matter, I'm describing the dispersal of the particles or the number of arrangements, and so as the forward reaction proceeds, entropy is decreasing, and that's why the sign of delta S is negative. Now let's take a look at part B of this question. In part B, it says, this reaction is thermodynamically favorable at 298 Kelvin. Which of the following represents the driving force for this reaction? Circle one of the following choices: delta H only, delta S only, or both delta H and delta S. Now on this next slide, this is something I had presented in my video for topics 9.1 to 9.6, and as you can see, it says driving forces that support the thermodynamic favorability of a process. So you can think of a driving force as a feature of a physical or chemical process that helps to explain why that process is thermodynamically favored to occur. And there are 2 possibilities for a driving force. If the process is exothermic, that is, delta H is negative, then this could be a driving force to explain why the process is thermodynamically favored to occur. If the process involves an increase in entropy, that is, delta S is positive, this could be a driving force to explain why the process is thermodynamically favored to occur. And another way to think about the driving force of a process is to look at the signs of delta H and delta S for that process and ask yourself the following question. Does the sign of delta H or delta S cause the value of delta G to be negative? So here we have the Gibbs free energy equation, and we'd like the delta G to be negative. So a negative delta H or a positive delta S would cause the value of delta G to be negative. And then at the bottom of this slide, it says, well, if the process is endothermic, that is, delta H is positive, then this cannot be a driving force to explain why the process is favored to occur. And if the process involves a decrease in entropy, that is, delta S is negative, again, this cannot be a driving force to explain why the process is favored. So to summarize, possible driving forces include a negative delta H and a positive delta S. And so what do we have in this particular situation? Well, we do have a negative delta H, but we have a negative delta S. And so in the answer to part B, it's going to be delta H only is considered to be a driving force. Now, in part C of this question, it says, justify your choice in part B in terms of the standard free energy change, delta G, and the signs of delta H and delta S for the reaction. So what I'm going to do at the bottom of this slide is simply answer part C by summarizing what I've already mentioned. So in part C, I said, reactions are thermodynamically favorable when delta G is negative. So a negative delta H value helps to make delta G negative, and so therefore a negative delta H value can be a driving force. But a negative delta S value does not help to make delta G negative, so a negative delta S cannot be a driving force. Now let's take a look at part D of this question. It says, although this reaction is thermodynamically favorable at 298 Kelvin, it is observed that the reaction occurs at a very slow rate. So part D falls under topic 9.4, thermodynamic and kinetic control. And so what's highlighted on this slide, it says processes that are thermodynamically favored but do not proceed at a measurable rate are under kinetic control. And it says that high activation energy is a common reason for a process to be under kinetic control. So now in part D, we can see that a common explanation for the slow reaction rate is the following. The value of the activation energy, or E sub A, for this reaction has a relatively high magnitude. It goes on to say that when a suitable catalyst is added to the reaction mixture at 298 Kelvin, it is observed that the reaction rate increases. Now, this would actually fall under Unit 5, or kinetics. So take a look on this next slide. This is from topic 5.11. Again, Unit 5 was on kinetics, or reaction rates, and 5.11 is catalysis. So what's highlighted on this slide says, in order for a catalyst to increase the rate of a reaction, the addition of the catalyst must increase the number of effective collisions and or provide a reaction path with a lower activation energy relative to the original reaction coordinate. So here in part E, if a suitable catalyst is added to the reaction mixture, the magnitude of the activation energy for the reaction will decrease. Now on this next slide, this is something I had presented in my lesson or my video for Unit 5 talking about catalysis, and you can see that a catalyst does not change the potential energy values for either the reactants or the products. So we do have an alternate pathway with a lower activation energy, but the difference in energy between the products and the reactants will remain the same. And so that's why in part F, if a suitable catalyst is added to the reaction mixture, the value of the standard free energy change, or delta G, for the reaction will remain the same. Now let's take a look at question 3. In question 3, it says, answer the following questions related to the reaction represented by the equation shown above. The value of the standard free energies of formation of the substances involved in the reaction are given in the following table. Part A, use the data in the table to calculate the value of the standard free energy change, or delta G, in units of kilojoules per mole of reaction for the reaction. So this falls under topic 9.3, but instead of using the Gibbs free energy equation that looks like delta G equals delta H minus T delta S, we're going to use a different equation. We're going to use the one involving products minus reactants involving the standard Gibbs free energy of formation. And as you can see here, this is one of the equations that is included on the AP Chemistry equations and constant sheet. So remember, just like I had mentioned in question 1 of this packet, don't forget to include the coefficients from the balanced chemical equation when you set up this calculation for products minus reactants. So the number for nitrogen dioxide, or NO2, that's 51.3, we're going to have to multiply that value by 2 because we see a coefficient of 2. So products minus reactants, it's going to be 2 times the number for NO2, so the standard free energy of formation, and then minus the number for N2O4, the reactant, which is 99.8. So when we do this math, products minus reactants, we get a value of 2.8. So the answer is positive 2.8, and the units are kilojoules per mole of reaction. Now let's take a look at part B of this question. It says, is the reaction thermodynamically favorable under standard conditions? Justify your answer. So remember that if the sign of delta G is negative, the forward process is thermodynamically favored to occur, but if the sign of delta G is positive, the forward process is not thermodynamically favored to occur. So the answer to part B is that the reaction is not thermodynamically favorable under standard conditions because the sign of delta G is positive, or that delta G is greater than 0. Now let's take a look at part C of this question. In part C, it says, calculate the value of the equilibrium constant, Kp, under standard conditions at a temperature of 298 Kelvin. So this question falls under topic 9.5, free energy and equilibrium. And what you can see highlighted on this slide are 2 different equations. It says the equilibrium constant is related to free energy by the following equations. Now, I just wanted to remind you that even though you see 2 different equations listed on this slide for topic 9.5, only one of these equations is actually listed on the AP Chemistry equations and constant sheet. And that's the one that says delta G equals negative R, the ideal gas constant, times T, the Kelvin temperature, times the natural log of the equilibrium constant K. So that first equation that's listed on this slide, the first equation is simply a mathematical rearrangement of the second equation. So when you need to solve for the value of the equilibrium constant K, you're just using a mathematical manipulation of that second equation. And then one more thing to mention with respect to the ideal gas constant R. If you look on this section of the AP Chemistry equations and constant sheet, you can see that there are 2 different numerical values of the ideal gas constant R, but involving delta G equals negative R times T times the natural log of K, you want to use joules. So the one that I'm highlighting on this slide, R equals 8.314 joules per mole per Kelvin. That's the one you want to use. You would use that other version of the ideal gas constant when you were solving for the traditional ideal gas law problems, such as the volume in liters, the pressure in atmospheres, the temperature in Kelvin, things like that. So I'm going to cross off that version. Let's go ahead and take a look at how we do this particular calculation. So on this slide is something I had presented in my video that included topic 9.5. When doing calculations involving delta G equals negative RT natural log of K, pay attention to the following. Choose the correct value of the gas constant R, that is, R equals 8.314 joules per mole per Kelvin, and the units of R are joules per mole per Kelvin, but the units of delta G are usually given in units of kilojoules per mole of reaction. So watch out, you have to convert either kilojoules to joules or vice versa, so make sure that the units match up. At standard conditions, temperature is often listed as 298 Kelvin. And then be careful with the signs of numbers in your calculations and in your final answer. So here on this slide is a example calculation, and the delta G for this example calculation happens to be negative 142 kilojoules per mole of reaction. So take a look at what I did. There's already a negative in the exponent, so a negative times a negative is a positive, and then I changed from kilojoules to joules so that the units of joules would be matching on the top and the bottom of this ratio. So that's why I have 142,000 joules per mole of reaction, and on the bottom I have 8.314 joules per mole Kelvin, as well as the 298 Kelvin. So when I do that math, I get E raised to the rather large number. It was 57.3. So look at that value of K. That's a very large value of K, indicating that this reaction essentially goes to completion. So when a reaction is thermodynamically favored from left to right, you have a value of K that is greater than 1. So if the delta G is negative, the value of K is greater than 1, favoring the products. On the other hand, if the value of delta G is positive, then that would mean it's not thermodynamically favored from left to right, but rather is favored in the opposite direction. And that would favor the reactants, or that K is less than 1. Let's go back and look at our specific question here in part C. So we know the delta G from part A of this question. That's positive 2.8 kilojoules per mole of reaction. So here's my setup. I have that the equilibrium constant is equal to E raised to the power negative delta G over RT. So take a look at what I'm doing here. I have changed the 2.8 kilojoules to 2,800 joules by multiplying by 1,000. Now my units are matching up, so I have joules on the top and the bottom. There was a negative in the exponent, so you can see that featured. And when I do that math of negative 2,800 divided by 8.314, and then also divided by 298, I get negative 1.13. And on my calculator, when I do E raised to the negative 1.13, I get an answer of 0.32, and that is the value of the equilibrium constant Kp. Now, remember that it said in topic 9.5 that processes with a positive delta G favor the reactants, and that K is less than 1. That's exactly what we see in this example. We have a positive delta G, and our value of K is less than 1. Now let's take a look at question 4. In question 4, it says the value of the equilibrium constant, Kp, for a certain chemical reaction varies with temperature as shown in the table above. Use the information in the table to answer the following questions about this chemical reaction. Part A, circle the correct choices for the substances that are favored at equilibrium in this reaction at temperatures of 300 Kelvin and 500 Kelvin. Assume that delta H and delta S are independent of temperature. Now, to answer part A, this actually goes back to unit 7, which is equilibrium. So here we have topic 7.5, magnitude of the equilibrium constant. And so what we learn is that a K value can either be large or small. And so when the K value is very small, or less than 1, the reactants are favored at equilibrium. And on the other hand, if the value of K is very large, or greater than 1, then the products are favored at equilibrium. So based on the information in the table here in question 4, we can see that at 300 Kelvin, the value of K is less than 1, so the reactants are favored. And at 500 Kelvin, the value of K is greater than 1, so the products are favored. So reactants are favored at 300 Kelvin, the products are favored at 500 Kelvin. Now, moving on to part B of this question, it says, identify the sign of delta G for this reaction at 300 Kelvin and 500 Kelvin. Assume that delta H and delta S are independent of temperature. So part B, that falls under topic 9.5, free energy and equilibrium. So if delta G is negative, then the system would favor the products, and that is K would be greater than 1. And if delta G is positive, then the system would favor the reactants, and K would be less than 1. So at a temperature of 300 Kelvin, K is less than 1, the reactants are favored, and that means that the sign of delta G for the reaction at 300 Kelvin would be positive. But then at a temperature of 500 Kelvin, now K is greater than 1, the products are favored, and so the sign of delta G for the reaction at 500 Kelvin would be negative. So what's happening is this reaction is switching from being not thermodynamically favored at 300 Kelvin, and then it becomes thermodynamically favored at a higher temperature of 500 Kelvin. So when the temperature is increased from 300 Kelvin to 500 Kelvin, this reaction switches from being not favored to favored. So here in part C, it says, identify the signs of delta H and delta S for this reaction. Assume that delta H and delta S are independent of temperature. So this goes back to topic 9.3, Gibbs free energy and thermodynamic favorability. And you can see that chart in which if we look at the sign of delta H and the sign of delta S, then we can make a decision about whether it is favored at all temperatures, no temperatures, high temperatures, or low temperatures. So what's happening is that because it switches from being not favored to favored as we increase the temperature, that would suggest that this reaction is favored at high temperatures. So we're looking for a positive delta H and a positive delta S. So that is my answer to part C of this question. Positive delta H, positive delta S. Now, we do have to justify our choices in part C in terms of the Gibbs free energy equation and then the answer to part B. So in part B, we said that the sign of delta G was positive at 300 Kelvin and negative at 500 Kelvin. So here's our Gibbs free energy equation. At 300 Kelvin, delta G is positive. 500 Kelvin, delta G is negative. So it's all because of that increase in temperature. So focusing on the T delta S term, if we increase the temperature, a higher temperature would increase the magnitude of the T delta S term in the Gibbs free energy equation. And because it switches from positive to negative, that means that the sign of delta G is becoming less positive or more negative when we raise the temperature. So a higher temperature causes delta G to become more negative. So mathematically, that means that the sign of delta S must be positive for that to occur. Well, now that we know that the sign of delta S is positive, let's consider delta H. So suppose, for an example, that the sign of delta H is negative. Let's take a look at this chart. If the sign of delta H were negative and the sign of delta S is positive, it would be favored at all temperatures. But that's not what's happening. It's actually switching from being not favored to favored when we raise the temperature. So the scenario is actually this, where we have it's positive delta H, positive delta S, and then this reaction is favored, but not at all temperatures, only at high temperatures. I'm going to go ahead and summarize what I just mentioned. So based on that information, here is my answer to part D. Justify your choices in part C in terms of the Gibbs free energy equation and your answer to part B. So here's my answer to part D. Delta G becomes less positive or more negative as the temperature increases. So therefore, the sign of delta S must be positive. And then if the sign of delta H were negative with a positive delta S, well then the reaction would be favored at all temperatures. But that's not what's happening. Under these conditions, it's only favored at high temperatures. So that means that the delta H must be positive and the delta S is positive, and therefore the reaction is favored, but only at high temperature. And now the last part of this question, part E, circle one of the following choices that best describes the thermodynamic favorability of this reaction. It's going to be favored at high temperatures. Now let's take a look at question 5. In question 5, it says, aluminum hydroxide is produced according to the equation below. Two half reactions and standard reduction potentials are given in the following table. Part A says, in the table below, write the modified versions of half reactions 1 and 2 that will produce the overall reaction when they are added together. So this question falls under topic 9.9, cell potential and free energy. The standard cell potential of electrochemical cells can be calculated by identifying the oxidation and reduction half reactions and their respective standard reduction potentials. So in order to answer part A, we have to figure out how the half reactions must be modified so that when we add them together, they will produce the overall reaction. So I'm going to start with the first reactant that I see in the overall reaction, and that is 4 moles of aluminum. So in half reaction number 1, I see 1 mole of aluminum, and it's actually on the right side of the equation, but I need there to be 4 moles of aluminum on the left side of the equation. That means that the modification for half reaction number 1 is to reverse it and multiply by 4. And so when I reverse half reaction number 1 and multiply it by 4, I get 4 moles of aluminum on the left, and then 4 times 3, that would be 12 moles of hydroxide on the left. And then on the right side of the equation, that would be 4 moles of aluminum hydroxide and then 12 moles of electrons. Now, moving on to the next reactant in the overall reaction, I see 3 moles of oxygen on the left. And in half reaction number 2, there is oxygen on the left side of the equation, but I need the coefficient to be a 3. So the modification for half reaction number 2 is to multiply each and every coefficient by the number 3. So I have 3 moles of oxygen, and then 3 times 2, that would be 6 moles of water, and then 3 times 4, that would be 12 moles of electrons, and then on the other side of the equation, that would be 3 times 4, so 12 moles of hydroxide ions. So now, considering that there are substances that appear on opposite sides of the equations that can be canceled out, I can cross off the 12 moles of hydroxide ions on opposite sides of the equation, and I can also cross off the 12 moles of electrons on opposite sides of the equation. So when the modified version of half reaction number 1 is added to the modified version of half reaction number 2, it does produce the overall reaction. So that is my answer to part A of this question. Now, in addition to the balanced chemical equation for each of these half reactions, we were also given in the table the value for the standard cell potential for each of these half reactions. And considering the fact that each of these half reactions has been modified in some way, 2 important questions for us to consider right now are the following. First, when the equation for a half reaction is reversed, how will the value of the cell potential be affected? And second, when the equation for a half reaction is multiplied by a constant n, how will the value of the cell potential be affected? So on the next slide here are some guidelines for manipulating half reactions. When combining 2 different half reactions to produce the overall equation for a redox reaction, the total number of electrons gained should be equal to the total number of electrons lost. And if we go back and take a look at our answer to part A, we can see that that is true, that we have 12 electrons gained in the modified version of half reaction 2, and then we have 12 electrons lost in the modified version of half reaction number 1. So that's good. That definitely agrees with the total number of electrons gained should be equal to the total number of electrons lost. Now, what about the changes? Well, if a half reaction is reversed, the sign of the cell potential is reversed, but it's important to understand that multiplying a half reaction by a constant n does not change the value of the cell potential. That's an important concept to understand. So considering the fact that half reaction number 1 was both reversed and multiplied by 4, all we're going to do to the value of the cell potential is change the sign. So the modified version of half reaction number 1 now has a cell potential of positive 2.31 volts, but we're not going to multiply that value by 4. And then for half reaction number 2, we multiplied all of the coefficients by 3, but this does not affect the value of the cell potential, so it's still positive 0.40 volts. And if we add these two equations together, we can add the cell potential values together. So 2.31 plus 0.40 gives us a value of 2.71 volts for the overall reaction. And so this is the answer to part B of this question. It says calculate the standard cell potential in units of volts for the overall reaction. So it's going to be 2.31 plus 0.40, which gives us a value of 2.71 volts. Now in part C of this question, it says, based on your answer to part B, which is positive 2.71 volts, calculate the value of the standard free energy change, delta G, in units of kilojoules per mole of reaction for the overall reaction. So if we look at one of the essential knowledge statements for topic 9.9, cell potential and free energy, we can see that the delta G, the standard Gibbs free energy change, is proportional to the negative of the cell potential for the redox reaction from which it is constructed. So you can see on the AP Chemistry equations and constant sheet, there is that equation listed where delta G is equal to negative N. N represents the number of moles of electrons that are transferred in the redox equation, times the letter F, which is the Faraday's constant, 96,485 coulombs for every 1 mole of electrons, and then times the standard cell potential. So here are some general guidelines for calculations involving this particular equation. If the standard cell potential is positive, then we expect that the delta G to be negative. But on the other hand, if the standard cell potential is negative, then the sign of delta G is positive. And that variable N in this equation represents the total number of moles of electrons transferred in the overall balanced equation for the redox reaction. And the Faraday constant is 96,485. The units are coulombs per mole of electrons. So because we've already added these two modified versions of the half reactions together, we can see that 12 moles of electrons were both lost and gained, so the N in this calculation will be 12. So I have delta G equals negative N times F times E, where that would be negative 12 moles of electrons, times the Faraday constant, which has units of coulombs per mole, and then times the cell potential, which is positive 2.71 volts. So when I pick up my calculator and do negative 12 times 96,485 times 2.71, I get a rather large number on my calculator. But what are the units of this number? So let's go back and take a look at the guidelines for calculations involving this equation. So 1 coulomb multiplied by 1 volt is equal to 1 joule. So that means that when I did this math just now and got a really large number, that's actually in units of joules per mole of reaction. But in part C, it said to calculate the value of delta G in units of kilojoules per mole of reaction. So I'm going to divide this number by 1,000 because there's 1 kilojoule for every 1,000 joules. And when I do that math, dividing by 1,000, and I round this number off to 3 significant figures based on the fact that the cell potential has 3 significant figures, and 12 is actually an exact number that doesn't have any limit on my precision, I've taken that number, 3,137,692, I've divided by 1,000, rounding it off to 3 significant figures, and I get my answer to part C, that the delta G is equal to negative 3,140 with units of kilojoules per mole of reaction. Now let's take a look at part D of this question. It says, the standard enthalpy change, or delta H, for the overall reaction is negative 3,393 kilojoules per mole of reaction. Based on this information and your answer to part C, calculate the standard entropy change, or delta S, in units of joules per Kelvin mole of reaction for the overall reaction at 298 Kelvin. So in order to answer part D, we're going to use the Gibbs free energy equation that looks like this. Delta G equals delta H minus T delta S. We know the value of delta G because that's our answer that we calculated in part C. We know the value of delta H because we were given that value in this part of the question, and then the temperature is 298 Kelvin. So if we plug in everything that we know into the Gibbs free energy equation, the only thing that we don't know is the value of delta S. So now this just becomes an algebra problem. I'm going to solve for delta S. So the first thing I'm going to do is to add 3,393 to both sides of this equation. And so I get 253 kilojoules on the left side of the equation. And on the right side of the equation, I get negative 298 times delta S. So I'm going to divide both sides of the equation by negative 298. And so when I do that math, 253 divided by 298, and there's a negative sign there, I get negative 0.849. And the units are kilojoules per Kelvin mole of reaction. But the instructions in part D said that we were supposed to calculate the standard entropy change in units of joules, not kilojoules, but joules per Kelvin mole of reaction. So one final thing I have to do is convert from kilojoules to joules, and I will do that by multiplying by 1,000. So my final answer is negative 849, and my units are joules per Kelvin mole of reaction. Now let's take a look at question 6. In question 6, it says, answer the following questions related to the information shown above. Part A, use the information in the table to calculate the value of the standard free energy change, delta G, for reaction 3 in units of kilojoules per mole of reaction. So this particular question falls under topic 9.7, coupled reactions. And coupled reactions is very similar to a Hess's law type problem where you're adding two or more chemical equations together. And the reason why we do this with coupled reactions is that you have an overall goal to achieve an overall reaction that is thermodynamically favorable. So in this coupled system, the individual reactions, they share one or more common intermediates, but when you add them together, the sum of the individual reactions produces an overall reaction that is thermodynamically favorable with a negative value for delta G. So here we have reaction 1 involving calcium carbonate, or CaCO3, and that delta G is actually positive. So that's not thermodynamically favorable. And then we have reaction 2 involving carbon and oxygen, and that has a negative delta G, which is thermodynamically favorable. But now for reaction 3, we have to determine what the value of delta G is for that reaction. And hopefully you can see from the reactants and products that all we have to do is add reaction 1 and reaction 2 together, and then that will produce reaction 3. So if we add the delta G values together, that would be positive 131.1 for reaction 1, and then plus negative 394.4 for reaction 2. And again, the units would be kilojoules per mole of reaction. So if we do that math, we get negative 263.3 kilojoules per mole of reaction. So that's our answer to part A. And then in part B, all we're really doing is deciding if these reactions are not favorable or favorable based on the sign of delta G. So if the sign of delta G is negative, then the process is thermodynamically favorable, but if the sign of delta G is positive, then it's not thermodynamically favorable. So reaction 1 with a positive delta G is not favorable under standard conditions, but both reaction 2 and reaction 3 have a negative delta G, so they are classified as favorable under standard conditions. So the fact that reaction 3 is classified as thermodynamically favorable, that's consistent with what you can see here on this slide for topic 9.7, coupled reactions, that the sum of the individual reactions produces an overall reaction that achieves the desired outcome and has a negative delta G, indicating that the overall reaction is thermodynamically favorable. All right, well now let's go ahead and take a look at question 7. In question 7, it says, a student sets up a standard galvanic cell with a solid aluminum electrode immersed in a 1 molar solution of aqueous aluminum nitrate and a solid nickel electrode immersed in a 1 molar solution of aqueous nickel nitrate. Assume that the temperature is 25 degrees Celsius. 2 half reactions and standard reduction potentials are given in the table above. So this question falls under topic 9.9, cell potential and free energy. Electrochemistry encompasses the study of redox reactions that occur within electrochemical cells. Most electrochemical cells will fall into 2 categories. The first category would be reactions that are thermodynamically favored, resulting in a positive voltage. So that would be what we typically see for a standard galvanic cell, which is also known as a battery, in which the reaction has a positive voltage and is thermodynamically favored. But then the other category would be that they are thermodynamically unfavored. They have a negative voltage and they require an externally applied potential for the reaction to proceed. So that would be an example of an electrolytic cell. And you can often tell when you look at the diagram for an electrolytic cell, you can see in the diagram there's this external power source or a battery that is required for that reaction to proceed. The standard cell potential of electrochemical cells can be calculated by identifying the oxidation and reduction half reactions and their respective standard reduction potentials. So because it says in question 7 that a student sets up a standard galvanic cell, it's important to know that in a galvanic cell, which is different than an electrolytic cell, for a galvanic cell, the cell potential is positive. The standard cell potential is positive for the reaction that occurs in a galvanic cell. And remember that if a half reaction is reversed, the sign of the cell potential is reversed. And multiplying a half reaction by a constant n does not change the value of the cell potential. So we know that the overall cell potential for this galvanic cell should be positive. We also know that we have 2 reduction half reactions, and so one of them needs to be reversed because we have to have both a reduction and an oxidation half reaction for this to work. So which half reaction should be reversed so that the sum of these cell potentials will equal a positive number? Hopefully you can see that if we reverse the aluminum half reaction, that will change the cell potential from negative 1.66 volts to positive 1.66 volts. And that will give us a positive value when we add that to the other half reaction. Now, we're not going to reverse both of these half reactions. We have to reverse only one of them. So we have now reversed the aluminum. So that's a reduction reaction that has now become an oxidation half reaction. And then the nickel half reaction is going to remain unchanged. So we have a oxidation reaction for aluminum. We have a reduction reaction for nickel. Now we still have a problem in that we have 3 electrons in one of these equations and 2 electrons in the other. So before these 2 half reactions are added together, we need to make sure that the electrons lost are equal to the electrons gained. And since the least common multiple of 2 and 3 is 6, then I'm going to multiply the aluminum half reaction, which is the oxidation half reaction. I'm going to multiply that by 2, but remember that that does not change the value of the cell potential. So multiplying this equation by 2, we're not going to change the value of the cell potential. And then for the nickel, the reduction half reaction, I'm going to multiply that by 3. That way the electrons will cancel out. So for the aluminum half reaction, now my coefficients become 2, 2, and 6. And then for my nickel half reaction, now my coefficients become 3, 6, and 3. So again, we did not change the cell potential other than reversing the aluminum and changing the sign. We did not multiply the cell potential by 2 and 3. So if I add these 2 equations together, you can see that the electrons are now going to cancel out. So 6 electrons lost, 6 electrons gained. Now in part A, it says write the balanced net ionic equation for the reaction that occurs as this galvanic cell operates. So our answer to part A would be 2 moles of solid aluminum reacting with 3 moles of aqueous nickel 2+ ions, and then it produces 2 moles of aqueous aluminum 3+ ions, and then 3 moles of solid nickel. So that's our answer to part A. And then for the value of the standard cell potential, that would be positive 1.40 volts, because it was positive 1.66 for the half reaction that we reversed, and then plus negative 0.26. That gives us a value of 1.40 volts. So that's our answer to both part A and part B. Now in part C of this question, it says, identify the anode and the cathode in this galvanic cell. So whether we're talking about a galvanic cell or an electrolytic cell, it's still true that oxidation occurs at the anode and reduction occurs at the cathode. And this is the mnemonic device to help you remember that an ox and red cat. So oxidation occurs at the anode, reduction occurs at the cathode. Now here is the answer to part A. We know that the oxidation numbers for aluminum and nickel are changing. Let's see how they're changing. So for the aluminum, the oxidation number changes from 0 to positive 3. So that means that aluminum is being oxidized. Aluminum must be the anode because that's where oxidation occurs. And then for the nickel, its oxidation number is changing from positive 2 to 0. That means that nickel is being reduced, so reduction occurs at the cathode. So aluminum is the anode where oxidation occurs. Nickel is the cathode where reduction occurs. In part D, it says, on the diagram above, draw an arrow to indicate the direction of electron flow in the wire as the galvanic cell operates. So another important feature of a galvanic cell is the direction of electron flow. Electrons travel through the wire from the anode, where oxidation occurs and electrons are lost, to the cathode, where reduction occurs and electrons are gained. So because electrons are traveling through the wire from the anode to the cathode, then you might draw arrows along the wire in this direction. So there's the answer to parts C and D of this question. Now in part E of this question, we are given a particle diagram. It says, a solution of potassium nitrate, KNO3, is used in the salt bridge. The particle diagram shown at right represents an expanded view of the center portion of the salt bridge. Draw arrows in this diagram to indicate the direction of movement for the potassium ions and the nitrate ions in the salt bridge as the cell begins to operate. So it's important to understand that in a galvanic cell, in the salt bridge, the anions will move toward the anode, and the cations will move toward the cathode. So the anions are the negative ions, and the cations are the positive ions. So here, the NO3 minus anions will move toward the left, toward the anode. So I'm going to draw some arrows showing that the nitrate ions are traveling toward the left, toward the anode. And then the potassium, the positive cations, they're going to be traveling toward the cations, which would be moving toward the right. So I'll draw some arrows showing the potassium ions, the cations, traveling toward the right, toward the cathode. So that is my answer to part E of this question. Now, in part F, it says, as this galvanic cell operates over time, will the mass of the aluminum electrode, which happens to be the anode, decrease, increase, or remain the same? Justify your answer. So if oxidation occurs at the anode, then aluminum is changing from 0 to +3. The atoms of aluminum on that electrode are changing into aqueous ions. So that's going to cause the mass of the solid aluminum electrode to decrease over time, because the atoms of solid aluminum are now being converted into aqueous ions of aluminum 3+, which means that they will enter the solution, and that will cause the electrode to decrease in mass over time. So that's the answer to part F of this question. Now, in the next part of this question, it says, a second galvanic cell is set up with identical conditions to the first galvanic cell except for a change in the concentration of the aqueous aluminum ions in the half-cell container as shown below. So for galvanic cell number 1, the concentration of the aqueous aluminum ions and the concentration of the aqueous nickel ions are both 1 molar. But in galvanic cell number 2, while the concentration of the aqueous nickel ions remains at 1 molar, they have decreased the concentration of the aqueous aluminum ions to a value of 0.010 moles per liter. So in part G of this question, it says, calculate the value of the reaction quotient Q for galvanic cell number 2 at the moment that the cell begins to operate. So the reason why we need to calculate the value of the reaction quotient Q for galvanic cell number 2 is that galvanic cell number 2 is no longer at standard conditions. So in part G of this question, this falls under topic 9.10, cell potential under non-standard conditions. And you can see on this slide, I'm highlighting one of the essential knowledge statements for this topic. It says that the standard cell potential, which has the symbol capital E with that superscript 0, looks like a degree symbol, the standard cell potential corresponds to the standard conditions in which the value of Q, the reaction quotient, is equal to 1. Now, if we set up a standard galvanic cell and we just let it run over time, this is what happens. Over time, the system will approach equilibrium. Over time, the cell potential will decrease, and then eventually the cell potential reaches a value of 0. So when the cell potential is 0, then you have arrived at equilibrium where the value of the reaction quotient Q is equal to a very large number, and that would be equal to the equilibrium constant K. So if you reach equilibrium for a standard galvanic cell, at this point, the cell is dead. Now, what comes next would be a discussion of deviations. Okay, so deviations from standard conditions. And those deviations can take you in one of 2 different directions. They can take the cell further from equilibrium than Q equals 1, or they can take the cell closer to equilibrium than Q equals 1. So on this next slide, this is the diagram that I normally use to help students understand and analyze non-standard conditions for a galvanic cell. And you can see on this slide, I've got 4 different rectangles. There's a green rectangle, there's a blue rectangle, there's a red rectangle, and then finally there's a black rectangle. I'm going to start with the blue rectangle. So that represents standard conditions for a galvanic cell. The value of the reaction quotient Q is equal to 1, and the cell potential is equal to the standard cell potential. Now let me move over to that red rectangle. That's what normally happens as the cell runs over time. So anything that you can do that would cause the system to get closer to equilibrium than standard conditions results in the following. The value of Q is now greater than 1. So now you have more products than reactants, or for some reason you have fewer reactants than products. And so when Q is greater than 1, now the cell potential is less than the standard cell potential. And eventually, if we keep going, we move over to that black rectangle. Now you have arrived. You're at equilibrium. The cell is dead. The Q is a very large number. It's equal to the value of the equilibrium constant K, and the cell potential is 0. Now let me talk about that green rectangle. What if, under these non-standard conditions, you can move the cell further away from, so not closer to, but further away from equilibrium than standard conditions? Well, in that green rectangle, you can see that now the value of the reaction quotient Q is less than 1, and then the cell potential would be greater than the standard cell potential. So hopefully this diagram will help you to analyze where are we when we have a non-standard cell. Are we further away from equilibrium than Q equals 1, or are we closer to equilibrium than Q equals 1? And then one more thing I'd like to show you. This is simply the Nernst equation that's highlighted on this slide. This would be the Nernst equation that you can find on the AP Chemistry Equations and Constant sheet, and you can see that Q represents the reaction quotient. So that is the ratio of products over reactants for the reaction for a galvanic cell, for that reaction. And whenever you have the capital E, the E cell, that does not have that superscript 0, that would be non-standard conditions. Okay, let's go ahead and calculate the value of the reaction quotient Q in part G of this question. So here we have, in part G, we have to calculate the value of the reaction quotient for galvanic cell number 2. And so it's going to be products over reactants, like you would normally see for an equilibrium constant expression, but this is the reaction quotient Q. So products over reactants, and we do not count solids in this expression. So we have the concentration of the aqueous aluminum ions squared, because of the coefficient of 2, divided by the concentration of the aqueous nickel ions cubed, because we have a coefficient of 3. Let's plug in our values for galvanic cell number 2. So it's going to be 0.01 squared divided by 1 cubed. And when we do that math, we get a value of 1 times 10 to the negative 4 for the reaction quotient. Now let's go back to that diagram, and we realize that Q is less than 1. So this takes us farther away from equilibrium than standard conditions, because Q is less than 1, and therefore the cell potential will be greater than the standard cell potential. So now we have our answer to part G, which is that Q is equal to 1 times 10 to the negative 4, but this helps us answer part H of this question. Part H says, do you predict that the cell potential for galvanic cell number 2 will be less than, greater than, or equal to the value of the cell potential calculated in part B? And that was the standard galvanic cell number 1. So remember that if Q is less than 1, that means that we're farther away from equilibrium than standard conditions, and the cell potential will be greater than the standard value. So here's my answer to part H. The cell potential for galvanic cell number 2 will be greater than the cell potential for galvanic cell number 1. And the reason why is because the reaction quotient Q, which we calculated in part G, is less than 1. And this causes galvanic cell number 2 to be further from equilibrium than standard conditions, and this results in a cell potential that is greater than the standard potential. Now let's take a look at question 8. In question 8, we are given a diagram, and it says an external direct current power supply is connected to two graphite electrodes immersed in a container of molten lead bromide, which is PbBr2, as shown in the diagram above. As the cell operates, bromine gas is produced at one electrode. And you can see in the diagram, that would be the electrode where there are bubbles of gas. So bromine, Br2 gas is produced here. And then liquid lead or molten lead is formed at the other electrode. And you can see that the lead is produced at the other electrode. Two half reactions and standard reduction potentials are given in the following table. Now, this is not a galvanic cell. Because of the external direct current power supply, this is an example of an electrolytic cell. Electrical energy from an external power source, for example a battery, is required in order for this chemical reaction to occur. So the cell potential in an electrolytic cell is negative. So the overall cell potential for this electrolytic cell should be negative. Now, which of the half reactions from the table should be reversed? Remember, we need one reduction half reaction and one oxidation half reaction. So right now in the table, we have two reduction half reactions. So which of these half reactions should be reversed? Well, if we're trying to get a negative cell potential, then I think we should reverse the bromine half reaction, because that will change the cell potential from positive 1.07 volts to a value of negative 1.07 volts. But another, perhaps more obvious reason to reverse this half reaction is because we already know that Br2 is a product. And so if Br2 is produced, then we need to reverse that equation so that the Br2 appears on the right side of the equation as a product. So we're going to reverse the bromine half reaction, and then we're not going to change the lead half reaction. So we reverse one of them. That way we have an oxidation half reaction as well as a reduction half reaction. So the bromine half reaction was reversed. So now that's an oxidation half reaction. And then the lead half reaction remains as it is. That's a reduction half reaction. If a half reaction is reversed, then the sign of the cell potential is reversed, and the standard cell potential should be negative for what happens in an electrolytic cell. So positive 1.07 now becomes negative 1.07 volts because we reversed it. And then for the lead, we didn't change it, so it still remains at negative 0.13 volts. When we add these two half reactions together, we do in fact get a negative cell potential. So negative 1.07 plus negative 0.13, that gives us a value of negative 1.20 volts. And the overall net ionic equation is lead 2 plus 2 bromide ions, Br minus, and it produces lead and bromine Br2. So part A, write a balanced net ionic equation for the electrolysis reaction that occurs in the cell. That would be Pb 2 plus, so lead 2 plus ions, plus 2 bromide ions, Br minus, and then it produces lead, Pb, and bromine Br2. So that's our answer to part A. And for part B, it says write the net ionic equation for the half reaction that occurs at each electrode in this electrolytic cell. So as far as what happens at each electrode, oxidation occurs at the anode, reduction occurs at the cathode. Now, the content associated with oxidation reduction was actually first introduced in Unit 4, which is entitled Chemical Reactions. So here on this slide, you can see topic 4.7, Types of Chemical Reactions, and topic 4.9, Oxidation Reduction or Redox Reactions. So one of the highlighted essential knowledge statements is, in a redox reaction, electrons are transferred from the species that is oxidized to the species that is reduced. Now, to help you remember whether it's loss or gain of electrons, you can use the following mnemonic device, which is oil rig, and that would be OIL, so oxidation is the loss of electrons, and then RIG, reduction is the gain of electrons, to help you remember what's going on with oxidation and reduction. So back to part B of this question, we know that oxidation occurs at the anode, and we know that oxidation involves the loss of electrons. So the half reaction that involves the loss of electrons would be 2 bromide ions, so Br minus, being converted into a molecule of Br2, and you can see that electrons are lost in that half reaction. And then the transformation of lead ions into atoms of lead, that involves the gain of electrons. So reduction, in which electrons are gained, happens at the cathode. Oxidation, in which electrons are lost, happens at the anode. Now, moving on to part C, we already know the answer to part C. It says calculate the value of the standard cell potential in units of volts for the electrolysis reaction that occurs in the cell. So we know that the cell potential should be a negative number for an electrolytic cell, and we've already determined that that would be negative 1.20 volts. So it's because the negative 1.07 volts for the oxidation half reaction is added to the negative 0.13 volts for the reduction half reaction. So negative 1.20 volts is the answer for the overall standard cell potential for this electrolysis reaction. Now, in part D of this question, it says, based on your answer to part C, which is negative 1.20 volts, calculate the value of the standard free energy change, or delta G, in units of kilojoules per mole of reaction for the electrolysis reaction that occurs in this cell. So here in part D, we will use this equation that you can see on the AP Chemistry equation sheet, in which delta G, the standard Gibbs free energy change, is equal to negative N times F times the value of the standard cell potential. So N represents the number of moles of electrons that were transferred in the overall redox equation. F represents the Faraday's constant, and again, that symbol, capital E with that superscript 0, that is the standard cell potential. So here on this next slide are the general guidelines for calculations involving this equation. So if the standard cell potential happens to be negative, then the value of delta G will have a positive sign. And the variable N represents the total number of moles of electrons transferred in the overall balanced equation for the redox reaction. And on the equation sheet, we can see that the Faraday constant is 96,485 coulombs per mole of electrons. So remember that the electrons that are lost have to equal the electrons that are gained, and so we see that would be 2 electrons lost, 2 electrons gained. So N represents 2 in our calculation. So delta G equals negative N times F times E, where N represents 2 moles of electrons transferred, and then there's the Faraday constant, and then the cell potential, negative 1.20 volts. So I'm going to pick up my calculator, and it's going to be negative 2 times 96,485 times negative 1.20. And when I do that math on my calculator, I get a positive number. I get 231,564. But what are the units of this calculation? Remember that coulombs multiplied by volts equal joules. So right now, the value that I have is in units of joules per mole of reaction. But the instructions in part D said to calculate the value of the standard free energy change delta G in units of kilojoules per mole of reaction. So I'm going to convert from joules to kilojoules by dividing by 1,000, because there's 1 kilojoule for every 1,000 joules. And so when I do that math, and I'm going to round off my answer to 3 significant figures, because the cell potential has 3 significant figures. Again, the number 2 is an exact number that does not limit my precision. This becomes positive 232 and the units are kilojoules per mole of reaction. So positive 232 kilojoules per mole of reaction, that's my answer to part D. And now, moving on to part E of this question, it says an electric current of 3.00 amperes passes through the sample of molten lead bromide for a period of 7.50 minutes. Calculate the mass in grams of lead that is produced during this time period. So this question falls under topic 9.11, electrolysis and Faraday's law. Faraday's laws can be used to determine the stoichiometry of the redox reaction occurring in an electrochemical cell with respect to the following: number of electrons transferred, mass of material deposited, the current, the time elapsed, or the charge of ionic species. And you can see that that equation, capital I, is equal to lowercase q divided by lowercase t. That equation is listed in this section of the AP Chemistry equations and constant sheet. So capital I represents the current with units of amps. Lowercase q represents the electric charge in units of coulombs, and lowercase t represents the time in units of seconds. So 1 amp is equal to 1 coulomb per second. And obviously the value of the Faraday's constant might be relevant in a calculation like this: 96,485 coulombs for every 1 mole of electrons. So on the AP Chemistry equations and constant sheet, I represents the current in units of amps, Q represents the electric charge in units of coulombs, T represents the time in units of seconds, and the units of electric current are amps or amperes, which is 1 coulomb per second. So you can use that relationship to create a conversion factor. And the Faraday constant gives the relationship between moles of electrons and charge, so that 1 mole of electrons is equal to 96,485 coulombs. And the relationship between moles of electrons and moles of product formed in an electrolytic cell is related to the coefficients in the half reaction, and a few examples are shown below on this slide. Now, based on the information that we are given in part E of this question, let's go ahead and start with the total amount of time. So the period of time in this experiment was 7.50 minutes. So I'll start with 7.50 minutes. I would like to convert from this unit of time to another unit of time, and that would be going from minutes to seconds. So there are 60 seconds in 1 minute, and now we're going to convert from seconds into coulombs using the definition of the amp or the ampere. So there's 1 coulomb per second. That means if we have 3.00 amperes, that would be 3.00 coulombs of electric charge for every 1 second. Now, I'd like to convert from units of coulombs to moles of electrons, and I'll use the Faraday constant to do that. So for every 1 mole of electrons, that would be 96,485 coulombs. That's my next conversion factor, that 1 mole of electrons for every 96,485 coulombs. Now, here is the half reaction involving the formation of lead. So we're trying to figure out the mass in grams of lead that is produced during this time period. And there are 2 moles of electrons gained for every 1 mole of lead that is formed. So 1 mole of lead for every 2 moles of electrons. So we've gone from minutes to seconds. We've gone from seconds to coulombs of electric charge. We've gone from coulombs of electric charge to mole of electrons. And then from moles of electrons to moles of lead. All we have to do now is look on the periodic table and find that the molar mass of lead is 207.2 grams per mole. So from minutes to seconds, seconds to coulombs, coulombs to moles of electrons, moles of electrons to moles of lead, and then finally from moles of lead to grams of lead. Now when I pick up my calculator, it's going to be 7.50 times 60 times 3 divided by 96,485 divided by 2, and then finally times 207.2. And my answer will be in units of grams, which is what I want. So when I do that math on my calculator, I get a final answer of 1.45 grams of lead, and I rounded off my final answer to 3 significant figures based on the time, which has 3 significant figures, and then the current also has 3 significant figures. So my answer is 1.45 grams of lead would be produced during this time period. Now, this question, this is part E of question 8. This is the last question in the packet. So this is the end of the video. I hope that you found all of these answers and explanations helpful. Good luck studying for your Unit 9 summative assessment. Thanks for watching.